First, I would like to thank the organizers for this very wonderful meeting. So far, I have really enjoyed all the talks, and I'm also thankful to the organizers for giving me an opportunity to speak here. So I'm going to talk about unconventional superconductivity in a system which is still half-filled but strongly correlated. And the superconductivity is stabilized only because of the frustration of magnetic order. So this work is done mainly in collaboration with my former student Anvesha Chattopadhyay, Shauman Bag, who was a student with H.R. Krishnamurthy at IISER Bangalore, and H.R. Krishnamurthy. And these are some of the references where you can find these works published. So let me start with something very basic by looking at some of the known examples of unconventional superconductors. So we have seen superconductivity in these most popular high TC cuprates. Then we have superconductivity in p-nictides, organic superconductors, and very recently in magic angle twisted bilayer graphenes. So if you look at the phase diagram for all these materials, you will find that there are some very common features. So for example, the parent compound in all these materials is a strongly correlated antiferromagnetic Mott insulator. P-nictides are a bit of exception because the parent compound is not a Mott insulator, but they have antiferromagnetic spin density wave order, but the system still has moderate enough correlations. And very recently, we also have another set of materials where superconductivity appears when you start with a parent material which has a charge density wave order. So applying pressure induces two-dome superconductivity in these Kagome metals. We heard a very nice talk on this in the first day of the session by Ronny Thomale, and also one of our organizers, Yasir, has a lot of work on these materials. So in the previous materials which I showed, since the parent compound is an antiferromagnetic Mott insulator, the common understanding in the community is that the superconductivity appears because of the spin exchange interaction, which basically provides a glue for Cooper pairing. But in these type of materials, where the parent compound has a charge density wave insulator, of course the pairing is not coming from some kind of spin fluctuation, but it must be provided by some kind of charge fluctuations. Now, another common thing about all these materials is that the superconductivity appears when you dope the parent compound away from half filling, away from the commensurate filling. So for example, in cuprates, you have to dope it with oxygen, and as the whole concentration becomes sufficiently large, the system shows a transition from antiferromagnetic Mott insulator to superconductor, and same thing happens in p-nictides as well as in bilayer graphene. Now, there is a very important issue about this doping away from the commensurate filling, and that is that the commensurate filling always induces, the chemical doping away from the commensurate point actually induces some kind of disorder into the system and makes these materials really inhomogeneous. And why is it so? Because we are starting from a parent compound, which is a Mott insulator. So any kind of chemical doping will produce a potential which will not get screened easily, and the system feels a large inhomogeneous chemical potential. And this is very easily reflected in this STS experiments on high TC cuprates, which provide the local density of state map for these materials. And you can see that the superconducting gap has inhomogeneity on nanoscale. As you move from one point to another point, you see that the superconducting gap changes a lot. So it's very important to come up with theoretical and experimental solutions where one can have high TC superconductors without doping. And my today's talk is something along that line. So what I'm going to show you today is superconductivity in a half-filled ionic Hubbard model, where the system is strongly correlated and is at half filling, but still the system has enough charge dynamics such that once you frustrate the magnetic order, the superconducting phase can be realized. And the interesting feature about the superconducting phase is that on one side, it is sandwiched by a charge-sensitive wave band insulator. On the other side, you have antiferromagnetic Mott insulator. And once we have enough frustration against the magnetic order and the system has enough quasi-particles, the system shows superconductivity. So the starting point for us is a very simple variant of the Hubbard model, which is known as the Ionic Hubbard model. So the only difference compared to the Hubbard model here is that we have a staggered potential. So this model is basically defined on a bipartite lattice with two sublattices A and B, and then you have a staggered potential A and B on those sublattices, such that sublattice A always prefers to have doublons and sublattice B always prefers to have holes. Now, if you look at the non-interacting limit of this model, you can see that the system has a gap induced by the staggered potential because it basically doubles the unit cell and induces a charge density wave order into the system. And if the U is much larger than the staggered potential delta, then the system is we basically go back to the physics of the standard Hubbard model, and what we see is a Mott insulator. What we see is a Mott insulator basically with the antiferromagnetic order, and no double-ons and holons are allowed in this limit. So the physics of the large U limit of the Ionic Hubbard model and the large delta limit of the Ionic Hubbard model are very simple and straightforward. The interesting question is what happens when the two energy scales, the staggered potential and the chemical potential and the Hubbard interaction, are comparable to each other. And there have been lots of studies on Ionic Hubbard model in past using dynamical mean field theory, determinantal quantum Monte Carlo, coherent potential approximation, etc., in various dimensions, mainly in the intermediate correlation regime. And all of these studies have basically indicated towards the presence of some kind of conducting phases, correlated metals and magnetically ordered metallic and half metallic phases at in the intermediate regime of this model. The focus of today's talk is actually the strongly correlated limit of the Ionic Hubbard model. So this model has also been realized in ultra-cold fermions on optical honeycomb lattice, and for large delta limit, they could see a charge density wave order, and for the large Hubbard interaction case, they could see a Mott insulating phase, and there are some indications of a metallic phase when the staggered potential and the Hubbard interaction are comparable to each other. Now, other places where you can think of Ionic Hubbard model as the minimal model to describe the physics of a material is, for example, graphene on hexagonal boron nitride substrate. Now, because of the difference in energy of boron and nitride, even electrons on the graphene sheet will feel some kind of staggered potential. And so one can think of Ionic Hubbard model as the minimal model to describe the physics of these materials. And another set of materials where again one can think of Ionic Hubbard model as a minimal model is, suppose you think of a bilayer graphene in the presence of a transverse electric field. Then this transverse electric field will basically provide a potential difference between the two layers of this bilayer graphene, and that again acts as a staggered potential. So now coming to the strongly correlated limit of the Ionic Hubbard model, which is not explored too much. So one can of course think of a simple strongly correlated limit where the Hubbard U is the largest energy scale and dominates over the hopping as well as the staggered potential. But this limit is not very interesting. It basically gives back the physics similar to the strongly correlated limit of the half-filled Hubbard model, because holes and doublons are projected out from the Hilbert space at all the sides of the lattice. And as an effect, the hopping processes are completely projected out and the system has no charge dynamics. So if you do some kind of Schrieffer-Wolff transformation on this half-filled ionic Hubbard model in this limit, where Hubbard used the largest energy scale, you will see that it maps onto an effective Heisenberg model. And the only difference compared to the case of the half-filled Hubbard model is that now the spin exchange interaction has a non-monotonic dependence on the staggered potential. So one can actually look at the one can actually tune the Néel orders by tuning the ratio of U by delta. And this is what we saw in one of our earlier work, that the Néel temperature can be enhanced by bringing delta close to U within the limits of this calculation. So this phase diagram was obtained using dynamical mean field theory with CTQMC as the impurity solvent. But as far as this talk is concerned, the main message to take from this slide is that all the hopping processes are projected out in the half-filled ionic Hubbard model in this limit when U is the largest energy scale and the system does not have any conducting phases. Either it's a band insulator with a charge density wave order, or it is an antiferromagnetic model insulator. The limit of interest is which can give rise to conducting phases in the half-filled ionic Hubbard model is when the Hubbard interaction U is of the order of the staggered potential and both these energy scales dominate over the hopping term. So let's look at the single site energetics for this limit of the half-filled ionic Hubbard model. So as you can see here very clearly that now on one of the sublattice, holes will be the holes are energetically expensive, but on the other sublattice, doublons are energetically expensive. So if you think in terms of some kind of generalized Schrieffer-Wolff transformation for this model, basically holes should be projected out from your low energy Hilbert space on A sublattice, and on B sublattice, doublons should be projected out from your low energy Hilbert space. As an effect, if you want to create an electron now in the low energy Hilbert space of the A sublattice, so suppose I want to create an electron with a spin up, I can do it provided there is a downspin electron at that site in the A sublattice, because there are no holes allowed in the low energy sector on the A sublattice. Similarly, on the B sublattice, I can create an electron with a spin up only if there is no downspin electron already present on that site in the B sublattice. So basically one has to work with these projected Hilbert space where holes are projected out from the low energy Hilbert space on A sublattice and doublons are projected out only from the low energy Hilbert space of the B sublattice. Now, what happens as an effect of that? So now if you want to do a generalized Schrieffer-Wolff transformation, treating your hopping term perturbatively, because that's the smallest energy scale in your problem, you will see that it is very different from the half-filled Hubbard model, because not all the hopping processes are projected out. So for example, we can still have a hopping from A to B sublattice, which creates a doublon on A sublattice and a hole on B sublattice, because a doublon on A sublattice and a hole on B sublattice are energetically allowed states. Similarly, we can have a reverse process where you start with a doublon on A sublattice and a hole on B sublattice, resulting in single occupancies on the two sublattices. So these nearest neighbor hopping processes are still allowed even in this strongly correlated limit of the half-filled Hubbard model. And if you have the next neighbor hopping, which will play a very crucial role in stabilizing the superconductivity, as I will show you after a few slides, then again we can have a hopping of doublons within the A sublattice through the second neighbor hopping, and we have a hopping of holes within the B sublattice. So even at half filling in this strongly correlated model, there is enough charge dynamics in the system, and both the first order and the second neighbor hopping processes are allowed, although not all the hopping processes are allowed. Now there are some interesting correlated hopping of doublons and holes also taking place within A and B sublattice respectively through the higher order terms. So for example, there can be a hopping of doublon within A sublattice via spin flip or a spin preserved term on the B sublattice. And similarly, you can see a hopping of hole on the B sublattice via spin flip or a spin preserved term on the A sublattice. Now, so these terms are also kind of providing a next nearest neighbor hop, a second neighbor hop within A and within B sublattice for the doublons on A sublattice and the holes on B sublattice. But an important point to keep in mind is that these terms are particle hole symmetric and they do not cause any frustration of the antiferromagnetic order. So these kind of terms, first of all, are highly suppressed compared to the bare second neighbor hopping terms, and these terms will not help us in stabilizing the superconducting phase, as we will see after some slides. So the generalized TIFR transformation on this model at half filling basically gives us this very interesting effective low energy Hamiltonian where we have hoppings allowed, projected hoppings allowed on the nearest neighbor side, as well as projected hoppings allowed on the second neighbor sides, that is within A sublattice and within B sublattice. We have nearest neighbor spin exchange interaction, and we also have next nearest neighbor spin exchange interaction between the spins on the A sublattices only and the spins on the B sublattices, and then we have many higher order terms, trimer terms, and all which I showed you. So how can one go ahead and solve this effective low energy Hamiltonian? So one thing to notice here is that the projected fermion operators, which can create particles and annihilate particles on A and B sublattices in this strong correlation limit, they do not satisfy the standard Lie algebra of the fermions. So we cannot use so the Wick's theorem doesn't hold, and it's not possible to do any standard perturbation theory in terms of the C tilde and C double tilde operators, which I defined a few slides back. So generally the standard methods available are the numerical methods like relational Monte Carlo, and it can be maybe one can try some DMRG and some other methods. So we studied this model within two methods. So first of all, we will do the Gutzwiller projected renormalized mean field theory on the low energy effective Hamiltonian that we have obtained, and we also studied the large U and large delta limit of the Ionic Hubbard model using dynamical mean field theory with CTQMC as an impurity solver. And then we will try to compare the results from the two methods. So let me first try to show you the phase. If we switch off the second neighbor hopping, so we have only the first neighbor hopping and the Hubbard U and the staggered potential, which makes the model very different from the Hubbard model. And then we try to compare the results from the Gutzwiller projected mean field theory against the dynamical mean field theory solved within CTQMC as the impurity solver. So you can see that there is a qualitative consistency between the two methods. Okay, so the Gutzwiller projected renormalized mean field theory actually captures the correct trend of the basic of various physical quantities like the staggered magnetization on the two sublattices and the difference in density on the two sublattices, although it cannot provide the correct transition point. The transition point obtained from RMFT is of course larger compared to the one that one gets from the DMFT plus CTQMC calculations because of the missing quantum fluctuations in the RMFT calculation. And in the absence of next neighbor hopping, this is the phase diagram that we obtain, that there is a transition from a band insulator with the dominant charge density wave order to the Mott insulator with the antiferromagnetic phase order. There is a very thin half antiferromagnetic half metallic phase in between, and if one forcefully suppresses the antiferromagnetic order, then one can see a thin metastable superconducting phase as well in this limit. Now, in the absence of next neighbor hopping, the half-filled Ionic Hubbard model has been studied by other approaches also. So let me show you the comparison of the phase diagram that we obtained from DMFT plus CTQMC and the Gutzwiller projected renormalized mean field theory with these other calculations. So Watanabe and all studied the half-filled Ionic Hubbard model using the relational Monte Carlo, and they do see a direct transition from a band insulator to an antiferromagnetic Mott insulator. They also did a study in the presence of second neighbor hopping, but that second neighbor hopping was turned on only on one of the sublattices, not on both the sublattices. So we cannot compare their results for T prime non-zero with our calculations on T prime non-zero, because we turn on the second neighbor hopping on both the sublattices as it should be done. And there were also earlier, so the main point here is, at least in the absence of the next neighbor hopping, our Kurzweiler projected renormalized mean field theory as well as the DMFT plus CGPMC provide a phase diagram which is qualitatively consistent with the variational Monte Carlo study. There were also studies using slave boson mean field theory, which surprisingly showed superconducting, a stable, broad superconducting phase even at half filling in the large delta limit of the Ionic Hubbard model. So this is the only case which is not consistent with our phase diagram in the absence of next neighbor hopping. So now let's turn on the next neighbor hopping and see what interesting physics do we get. So the first thing to notice is, in the absence of next neighbor hopping, the non-interacting model has an indirect gap of the order of delta minus 40 prime. So even in the non-interacting case, one will get a metal by the time T prime approaches delta by 4. So the question is, what happens when you turn on the interaction? So before going to the strongly correlated phase of the Ionic Hubbard model in the presence of second neighbor hopping, let's see what happens when we have interactions which are moderately strong and are not really very strong. So here we have shown the phase diagram, again obtained within dynamical mean field theory plus CGPMC for delta equal to 2T and moderate strength of the Hubbard interaction. And as you can see that for a finite value of the second neighbor hopping, the system shows several transitions from charge density wave insulator to antiferromagnetic Mott insulator via the intervening paramagnetic metal phase, then a correlated ferrimetal phase, and then a antiferromagnetically ordered half metal phase. So none of these ferrimetal and antiferromagnetic half metal phase have ever been seen on half-filled Hubbard model in the presence of second neighbor hopping. So these are the specialty of the Ionic Hubbard model, and it happens because of the imbalance between the two sublattices. And so what are the features of this correlated metal, ferrimetal and half metal phase? To understand that, we calculate the momentum distribution function from DMFT plus CGPMC, which is shown here. And what we see is that in the paramagnetic metal phase, both the up and the downspin electrons have electron pockets around the pi by 2 points and hole pockets around the pi 0 points. And as you tune the electron interaction strength and go towards the ferrimetal phase, you will see that the electron hole pocket for one of the spin sector, for example the upspin sector here, has become much enlarged compared to that for the downspin sector. In fact, there are no hole pockets now in the downspin sector. So this is the ferrimetal phase where we have a net occupancy of the upspin is larger than the net occupancy of the downspin, but the neighboring spins are still antiparallel to each other. And then in the antiferromagnetic half metal phase, we see the Fermi pocket only in the upspin channel, and the downspin channel is completely gapped, resulting in an antiferromagnetic half metal phase. So although with the help of second neighbor hopping at finite electron-electron interaction, one can induce these ferrimetallic and antiferromagnetic half metal phases, but all these metallic phases are kind of compensated metals with very short Fermi pockets. They don't have a large connected Fermi surface. So this is something to keep in mind, that we are always getting a compensated metal even at the intermediate strength of the electron-electron interaction. And now we go to the limit of interest where we will see superconductivity. So let's look at the limit where the electron-electron interaction is comparable to the staggered potential, and both these energy scales are much larger than the hoppings involved in the model. And in this limit now, if we solve the effective low energy Hamiltonian that we obtain from a generalized TIFR-Wolff transformation using Kurzweiler projected renormalized mean field theory, we see that as you increase the strength of the next neighbor hopping, the strength of electron-electron interaction that you need to turn on the magnetic order increases with the next neighbor hopping. So that is very clearly visible here, that as you increase the electron-electron interaction from 0.1 to 0.45, you see that the transition point shifts towards right. This is clear indication of the fact that the next-neighbour hopping is providing frustration against the magnetic order, because if you remember, we had along with the nearest neighbor spin exchange term, we also have a next neighbor spin exchange term now in the model. And this frustration of the magnetic order and shifting of the critical point as you increase the strength of the next neighbor hopping actually helps in stabilizing the superconducting phase. Another interesting feature that happens as you increase the strength of the next neighbor hopping is that the range, that the uniform magnetization also turns on for a larger range of U by delta. It means that the system won't have only an antiferromagnetic order, but there is also a range of U by delta for which we see the ferrimagnetic order. Now let's look at the superconducting pairing amplitude. So this is the study on the 2D square lattice, and we looked at both the D wave and the extended S wave pairing amplitudes. And what we see is that one needs a finite strength of next nearest neighbor hopping to turn on any of the pairing amplitudes. So for example, the D wave pairing amplitude turns on only when the second neighbor hopping is larger than 0.1 times the nearest neighbor hopping, and the extended S wave pairing amplitude turns on when the second neighbor hopping is at least 0.35 times the first neighbor hopping. And as the strength of the second neighbor hopping increases, the range of U by delta over which the pairing amplitude remains non-zero that increases, and also the strength of the pairing amplitude increases. So this basically shows that the frustration of the, because the frustration of the magnetic order is actually stabilizing the superconducting phase. So you can see very clearly that the transition point at which the magnetic order sets in is also the point at which the superconducting order drops to zero. So only within the range of parameter where the system does not have any magnetic order, superconductivity survives. Then from the long range, off-diagonal long range order correlation function, one can also calculate the superconducting order parameter. And what we see is that the superconducting order parameter for D wave and extended S wave is much smaller than the pairing amplitude, indicating the possibility of a pseudo gap phase in this superconducting model. Now, one point to emphasize here is that although the extended S wave superconductivity turns on at a much larger value of T prime, but once it turns on, we have both the D wave and the extended S wave as the viable solutions with very close by ground state energies. So both of them coexist in certain parameter region. So this is basically the phase diagram for a fixed strength of the second neighbor hopping. So once the second neighbor hopping is sufficiently large such that the system can sustain superconductivity by frustrating the magnetic order, this is the phase diagram you get. So as you move along as you increase the electron-electron interaction, the first thing that happens is that the gap in the charge density wave insulator gets closed and the system becomes a paramagnetic metal. As you keep increasing the strength of electron-electron interaction further, the D wave superconductivity turns on and it survives as long as the system does not become magnetically ordered. So there is a transition from D wave superconducting phase to a ferrimagnetic metal, followed up by a transition into an antiferromagnetic mode insulator as we keep increasing the strength of electron-electron interaction. And in between, there is a small range of electron-electron interaction where both the D wave and the extended S wave superconductivity are almost regenerate. Now, the interesting feature about this phase diagram is that the superconductivity is sandwiched by the paramagnetic metal and the ferri metal on the other side, although the superconductivity is mainly induced by spin exchange interactions in this model. So this is a complete zero temperature phase diagram, which I showed earlier also. So I'm just showing you different sections of the phase diagram. So now the electron-electron interaction has been fixed and I'm changing the strength of the second neighbor hopping. So you can see that for low values of the second neighbor hopping, system does not have any superconducting phase. And once the second neighbor hopping becomes large enough, the superconductivity is induced by frustration of the magnetic order. and there is this parameter regime where both D wave and extended S wave superconducting phase are almost regenerate. And the most interesting feature, as I'm showing you, is that the superconductivity on one side starts on a charge density wave insulator, and on the other side it starts from antiferromagnetic Mott insulator. But from either side you start, the transition into the superconducting phase takes place not directly from the insulator, but it always takes place via a metallic phase. So first the system gets, first the gap in the single particle excitation spectrum gets closed by either increasing the electron-electron interaction as you are coming from the charge density wave band insulator side, or by decreasing the electron-electron interactions if you are coming from the antiferromagnetic Mott insulator side. And once the system has become paramagnetic metal or ferry metal, and if it has enough number of Pauling particles, the system starts showing superconductivity. So all this is happening at half filling in the strongly correlated limit of the Ionic Hubbard model. Now, to understand why the system has to go via metallic phase to get the superconductivity to become a superconductor, we look at the low energy spectral functions of various metallic phases. So here I'm showing you the low energy spectral function for the up and down spin. The top layer is the up spin and the bottom layer is the down spin. And you can think of it as moving, say, from the ferry matter to the D wave superconductor. So when you start from the ferry matter at large U by delta, you see that the spectral function show on these small Fermi pockets. These are the electron pockets actually. And as you decrease the electron-electron interaction, it actually the electron-electron pocket starts becoming bigger, and at the point where the system transits into a superconducting phase, we see almost connected Fermi pockets. And similarly, you can see that if you start with the parametal phase on the left side of the superconductor and increase the strength of the electron-electron interaction, which is shown in the bottommost panel of this figure. So for the small electron-electron interaction, we have very tiny Fermi pockets. The system doesn't have enough number of quasi-particles in it. And as you increase the strength of the electron-electron interaction, the Fermi pockets become bigger in size, and eventually they almost start touching it, and that's the point where the superconductivity sets in. So the next second neighbor hopping is actually doing two things. First, it is providing a frustration against the magnetic order through the next neighbor spin exchange term, and it is also basically enhancing the dynamics of doublons and holes or holons on the A and B sublattices where they are allowed, and enhancing the charge dynamics and charge fluctuations. And the same thing you can see if you basically increase the strength of the second neighbor hopping, then what happens? So if you increase the strength of the, because we know that we need a finite strength of the second neighbor hopping for the superconductivity to appear in this strongly correlated half-filled model. So if you increase the strength of the second neighbor hopping, keeping the ratio U by delta fixed, again you see that at very small second neighbor hopping, the system has very small Fermi pockets, and these Fermi pockets become bigger as you increase the strength of the second neighbor hopping, and that's the point where we start seeing the superconductivity. And this is just the momentum distribution function consistent with the spectral functions, which shows that at the pi 1 and pi 2 points you have the electron pockets, and pi 0 points you have the Fermi pockets. Okay, so we also looked at the single particle density of states in all the metallic phases. And as you can see that in all the metallic phases, whether it's a parameter or a ferri matter, the density of state at the Fermi energy is very, very low and depleted, which is consistent with the fact that we had small Fermi pockets in these metallic phases, and these metallic phases are actually compensated metals. And And if you look at the density of state in the superconducting phase, so of course in the D-wave superconducting phase, you see a linear dispersion in the density of state, which is a characterization of normal quasi-particles in this phase. But interestingly, even in the extended S wave, we see the linear dispersion in the density of state. The linear behavior of the density of state at very small energy scale, which is because of the fact that we have these small electron pockets, Fermi pockets, where the superconductivity takes place. And at those small pockets, even for the extended S wave, the varying amplitude is has a lot. Now, if you look at the peak-to-peak spacing in the density of state for the superconducting phase, which gives you basically a superconducting gap. So this gap actually increases monotonically as a function of electron-electron interaction, both for the D-wave superconductivity as well as for the extended S-wave superconductivity. And but this gap, as you can see, is much larger than the superconducting order parameters, which again indicates that the system must be having a large pseudo gap phase. The superconductivity will be killed by loss of coherence as we increase the temperature, and there will be a depletion in the density of state even above TC because of the Cooper pairs which will survive even for T greater than TC. And the pseudo gap phase for the D-wave superconductor is much larger, should be much larger than the pseudo gap phase for the extended S-wave superconductors, because the gap for the extended S-wave superconductor is closer to the superconducting order parameter compared to the D-wave superconducting phase. So with this, I would like to conclude. So basically, I have talked about a simple variant of the Hubbard model, where just by inducing staggered potential and taking a very special limit of strong correlation, where the electron-electron interaction as well as the staggered potential are much larger than the hoppings in the system, it's possible to induce superconductivity even at half filling, provided the system has enough frustration against the magnetic order. And although the superconductivity is induced by spin fluctuations and by the spin exchange interaction term, interestingly, the superconductivity appears sandwiched between the paramagnetic metal and the ferromagnetic metal on both the sides, and which makes this phase diagram very different from the phase diagram of any known unconventional superconductor that we are familiar with today. Now, the big question is, are there any experimental realizations for this superconducting phase? So it would be good if experimentalists can look at the ultra-cold fermions, where this model has been realized on honeycomb lattice. And another possibility can be to look for layered or heterostructure materials, which I mentioned in the beginning of my talk. And so far we have studied this strongly correlated event only within Kutzler projected renormalized mean field theory, and some aspects we have studied using TMFT plus GPMC. So it's definitely, it would be good to have a solution from state-of-the-art methods for this model, like tensor networks, DMRG, and other tools. So with that, I would like to thank you.
Thank you very much, Arti, for this very nice presentation. We have time for a few questions. I don't see any questions, but I have maybe not too very nice question. So you were saying that the model is motivated by bilayer graphene or graphene on surfaces, right?
Yes.
It means that the model that you work on is geometric phase is found for parameter regime when the Hubbard U is approximately the same size as your staggered potential. So how realistic is that? Like, is it?
So the point I have in mind is that so the electron-electron interaction in graphene to start with is actually not very strong, and same is true for any staggered potential that will be induced by the transverse field or by the boron nitride. But if one can apply some kind of strain which can basically reduce the hopping and enhance the So if it reduces the hopping, then both the electron-electron interaction and the staggered potential will increase in a similar fashion. So that's I mean, it's just a possibility. I think it's a possibility and it needs to be explored. I'm not really claiming that we are providing a phase diagram for these materials, but I'm saying these kind of materials can be one of the possibility to realize this limit of the ionic Hubbard model, where one can really tune the strength of electron-electron interaction and any local chemical potential by applying a strain or a twist, which suppresses the hopping exponential.
Okay, thank you very much. Do we have any questions? The online participants? If not, then let us thank Arti one more time for this nice talk.